Welcome to The Explainer. I want you to think of me today as your resident geometer. We're going to keep things highly logical, precise, and educational right from the jump. Today, we are dissecting a piece of math that is quietly running the modern AI revolution. I mean, it is hidden inside your search engines, your recommendation feeds, and massive AI models like ChatGPT. We are talking about cosine similarity. But to truly wrap our heads around it, we first have to unlearn a deeply ingrained human bias about how we actually measure space and relationships.
So are we measuring distance or are we measuring alignment? Let's dive right into this. Since we were kids, we've relied on physical distance to judge how closely related two things are, right? If an apple is sitting right next to an orange on a table, well, they're close. If the orange is all the way in another room, they're far apart. We instinctively use a straight line, what mathematicians call Euclidean distance, to measure relationships. But here's the thing. In the crazy, high-dimensional spaces of artificial intelligence, relying on physical distance is a massive trap. We constantly have to ask ourselves, when we compare complex data, are we trying to measure the literal distance between them, or are we trying to measure their underlying alignment?
To really visualize why distance completely fails us here, picture this. Imagine a completely dark room. You and a friend are standing inside, and you both have literal laser pointers. You're both aiming at the exact same spot on a distant wall. But here's the catch. You are standing super close to that wall. Your arm is bent, and the laser beam you're projecting is really short. Your friend, on the other hand, is standing a mile away on the exact opposite side of the room. Their arm is stretched out perfectly straight, and their laser beam is incredibly long.
Now, if a computer uses Euclidean distance, that classic straight-line measurement we talked about, to figure out if you and your friend are pointing at the same thing, it's going to measure the literal distance between the physical tips of your laser beams. And because your friend is a mile away, the gap between the start of your short beam and the start of their long beam is massive. The computer looks at that huge gap and completely panics. It wrongly concludes that you two are pointing at completely different targets. It literally gets fooled by the length of the beams. But cosine similarity? It couldn't care less about the length. It completely ignores it. It only looks at the angle between your two arms.
And that brings us to the absolute golden rule for this explainer. We aren't measuring distance, we are measuring alignment. Once you really internalize this, everything about vector embeddings just clicks. It literally does not matter if one laser beam is 10 feet long and the other is a mile long. The length, or the magnitude as we call it, does not equal alignment. If both beams are locked onto the exact same target, they are semantically identical. Period. Because both of your arms are pointing at the exact same spot on that building, the angle between your arms is 0 degrees. There's no deviation whatsoever. And if you reach back to your high school trigonometry days, you might remember that the cosine of 0 degrees is exactly 1. In the world of machine learning, a cosine similarity of 1 means perfect similarity. You are perfectly aligned. Now, on the flip side, if you pointed at the wall and your friend pointed straight down at the floor, you'd have a 90-degree angle. The cosine of 90 is 0, which correctly tells the computer that you two are entirely unrelated.
So how does this translate into real-world information retrieval? Well, imagine we aren't comparing laser pointers anymore, we're comparing documents. Say you have a crisp 10-word text summary of a concept, and you want to match it to a massive 1,000-word textbook chapter that covers that exact same concept. Inside a computer, these texts are turned into vectors based on things like word frequencies. Now, the chapter obviously has way more words, so its vector is massive. It has a huge length, a huge magnitude. Just like that long laser beam, Euclidean distance would look at these two highly related documents and declare them completely different simply because one is longer. Cosine similarity saves the day here by completely ignoring the word count and looking only at the semantic direction. So, here is the crucial question. How do we mathematically force the computer to ignore that length? We use a process called normalization. Picture a 3D space with a giant cloud of vectors floating around in it. Some are tiny little arrows, some are massive spears shooting way off into the distance. They are raw, they're noisy, and they are all completely different lengths. Now imagine a visual projection where every single one of those arrows magically shrinks or grows until their tips perfectly touch the surface of a single, perfectly round bubble right in the center of the space. That bubble is the unit sphere. All those vectors now have the exact same length of 1. To get them onto that unit sphere, we divide each vector by its L2 norm, which is really just the exact Euclidean length of the vector itself. By dividing a vector by its own length, we are stripping away the noise of magnitude. It is an incredibly satisfying mathematical cleanup process. We are removing the noise to reveal the pure signal of direction. That massive 1,000-word textbook chapter and the tiny 10-word summary are scaled so they sit perfectly right alongside each other on the surface of that sphere.
Now this is where it gets really cool, especially if you write code. Notice the contrast here between the mathematical theory and the actual PyTorch reality that engineers use. On the left, you've got the formal math, the dot product of two vectors divided by the product of their L2 norms. It looks a bit heavy, right? But look at the code on the right. In production, you don't actually compute that whole fraction at once. You use f.normalize on your inputs first. That handles the entire denominator, snapping everything right to the unit sphere. Then you just use the @ symbol, which is PyTorch's shorthand for a dot product matrix multiplication. The normalization is literally just the denominator of the math formula, applied to the inputs before the dot product even happens.
And why do we do it in this order? Honestly, it is sheer computational genius. Because we pushed our vectors onto the unit circle first, their lengths are exactly 1. And 1 multiplied by 1 is, well, 1. That means the entire messy denominator of our complex fraction completely disappears. Once your vectors are normalized, calculating cosine similarity is literally just calculating the dot product. We completely eliminate those slow, element-wise division operations and unleash blazing fast GPU matrix multiplication. This one mathematical trick is the only reason we can search through millions of documents in literal milliseconds.
And this lightning-fast mathematical engine? It lives absolutely everywhere in modern AI. Dense retrieval systems, like those RAG architectures everyone is building, use it to match your search query to massive databases of L2 normalized documents. Vision language models like CLIP use it to perfectly align the embeddings of images with the text that describes them. Even face recognition models, like ArcFace, use angular margins in cosine space to mathematically push different human identities apart. It scales so effortlessly across all these different domains precisely because it relies on pure geometric alignment. But hold on, we do need to be careful here, because there is a very common beginner trap in AI engineering. It's really tempting to think that transformers' self-attention, the core brain inside models like ChatGPT, uses cosine similarity. It actually does not. Attention uses a scaled dot product, without any L2 normalization. Why? Because in self-attention, the magnitude actually holds vital information. If a token is highly confident or important, its vector length is physically larger. If we normalized it, we would completely destroy that confidence signal. So remember, cosine similarity strips magnitude away. Self-attention strictly preserves it.
Because, misunderstanding when to use this tool leads to some pretty severe failure modes. The most notorious one is the zero vector bug. If you try to normalize a vector of all zeros, like blank padding tokens in a sequence, you end up dividing by 0. This creates not-a-number errors that will instantly destroy your model's weights. Gone. Then there's the curse of dimensionality. In massive, say 4,000-dimensional space, random vectors naturally push apart and become almost perfectly 90 degrees orthogonal. That makes all your cosine similarities round to 0, which totally kills your training gradients. And finally, using it for something like anomaly detection can be disastrous if the sheer scale or magnitude of a sensor reading is the actual anomaly.
Which brings me to a final thought I want to leave you with today. We have spent this entire explainer stripping away magnitude, treating length like this annoying distraction so we can find true semantic alignment. But geometry is all about context. If magnitude is just noise when we are searching for meaning in language and images, when does it become the crucial signal? When does the length of the laser beam actually matter more than where it's pointing? As you continue your journey into AI, always ask yourself, are you looking for the angle or are you looking for the distance? Thanks for exploring the math with me today. See you next time.